All right. In this video, we'll talk about mechanisms in heterogeneous catalysis. So we can't get through a class on chemical reaction engineering without talking about mechanisms. So we could talk about mechanisms using various examples. I think using heterogeneous catalysis is a good way to talk about it because the mechanisms tend to be a little bit more straightforward. And because catalysis is so prominent in the chemical industry. So if we consider a heterogeneous catalyst, so we talked in the last video, that means that the catalyst is in a different phase than the reactants and products. Usually the catalyst is a solid and the reactants and products are gases and or liquids. So thinking about a reaction occurring on a catalytic surface, we'll just take our simple example reaction. A goes to B, and we're just going to say it's happening on a heterogeneous catalyst. So there are at least 3 steps that would happen. So the reaction mechanism is going to be comprised of at least 3 steps. First step, A is going to adsorb to the catalyst surface. In the second step, A is going to react to B on the catalyst surface. And in the third step, B is going to desorb from the catalyst surface. So we can draw this out. So if I draw my catalyst surface, so we'll say catalyst surface. In the beginning, I'll have some amount of molecules of A flying around in the gas phase. Those molecules of A are going to adsorb or bind to the catalyst surface. So here we have, imagine a gas molecule A, it's flying around in the gas phase, it collides with the catalyst surface, and the energy with which it collides is sufficient such that it allows formation of a chemical bond between molecule A and the catalyst surface. And really that bond doesn't have to be chemical, it could be physical. So A adsorbs. Once A adsorbs, it can react to form B. So this is not a directional arrow, so the A doesn't, I'm not claiming here that A is moving along the catalyst surface, but A is reacting to form B. So on the surface, you have a molecule of A, and a reaction takes place to convert it into B. And then B desorbs from the catalyst surface. So it goes back into the gas phase. So you'll notice I drew these arrows both as double-sided arrows, and this is a single-sided arrow. I'll get to why I did that in just a moment. So the reaction mechanism is going to account for all 3 of these steps. So the reaction mechanism, the series of steps taken to get from reactants to products. In this example, our steps were, our first step is that A gas adsorbs to the catalyst surface. Our second step was that adsorbed A reacts to form adsorbed B. And then our third step was that adsorbed B desorbs from the catalyst. So in this notation, when we talk about heterogeneous catalysts, often we use an asterisk to denote catalyst site. So a catalyst site is a place on a catalyst surface where a species can adsorb. So a molecule of A here collides with and reacts with a catalyst site to form adsorbed A. So this species here is A bound to that catalyst site. Another way to write that would be, if, for example, and actually let me not do an arrow. So we can think of A star as A bonded to, for example, if our catalyst is platinum, we can say A bonded to platinum. So it's just kind of a way to denote a catalyst site. So in this mechanism, we incorporate all of our steps. We've taken into account catalytic sites and species bound to catalysts. So a catalyst surface is going to have some finite number of sites. So once those get all filled up, nothing can absorb anymore. So a way to keep track of that is how we call site balance. So what that means is my catalytic sites, you can think of those as chemical species, just like any of the other species here. So species A is a species, this asterisk, this catalyst site, that's also a chemical species. So just like in a chemical reaction, I must balance the number of molecules of A on the reactants and product side, I must also balance the number of catalytic sites. So if I write a catalytic site here, I also need one on my product side. So you'll see in each reaction I have a balance. So the number of asterisks on my products and reactant side is always equal. So the other thing you may notice about the way I wrote this mechanism, and I alluded to this before, but the arrows on my adsorption and desorption step I wrote as double-sided, whereas on my surface reaction step I wrote it as single-sided. So adsorption and desorption steps in a mechanism are often unactivated. This means that there is no activation barrier. In reality, there probably is an activation barrier, but it's usually not large compared to the activation barriers of the surface reactions. So because of that, we tend to just assume that adsorption and desorption is unactivated. So for example, if a typical activation barrier for a surface reaction is 80 kilojoules per mole, a lot of times a activation barrier for an adsorption or desorption reaction is going to be, and actually assuming, I shouldn't say adsorption or desorption, so we'll say an activation for an adsorption reaction, considering that the heat of the adsorption reaction, so the delta H of adsorption, is exothermic downhill, then the barrier to that reaction might be like 5 kilojoules per mole. So it's 16 times smaller than the surface reaction involved with that reaction mechanism. Because of that, it's never going to be, or under the conditions which the reaction is run, it's not going to be rate limiting. So the reaction is going to come into equilibrium, so we don't need to concern ourselves with that activation barrier. So in other words, we can say that we'll say adsorption and desorption steps are driven by thermodynamics and not kinetics. And there's, of course, exceptions to that rule. They are beyond the scope of this course. So because of that, if we have adsorption and desorption steps, and we're saying that pretty much they have very low barriers, and under catalytic operating conditions, they often come into equilibrium or quasi-equilibrium, that means that the surface reaction is often thus the rate limiting step. We'll say the rate. You can say rate limiting step, or another way that people refer to that is the rate determining step. And rate determining step is often denoted RDS, and probably there's you'll see some cases where rate limiting step is denoted RLS. So the rate limiting step or rate determining step is the slowest step in the mechanism. And when I say slowest, I'm talking now about kinetics. So thermodynamics, there is no time scale. You're already, your rate is equal to 0. Kinetics is what determines the rate. So when I say the slowest step, it has something to do with the rate of that particular reaction. And oftentimes, and always in this class, it's because the activation barrier is the highest. So slowest step in the mechanism. In other words, the bottleneck step. So if you think about a mechanism being a series of steps, the one that's causing the mechanism to go slowly or go slower than it could is this bottleneck, this step. So it defines the rate of reaction. Because of this, we often assume that if there's one rate determining step, one rate limiting step, the rates of all the other steps in the mechanism are fast enough to come into equilibrium. So we assume the RLS or RDS, same thing, is the only slow step in the mechanism. And all other steps we'll say can thus, we'll just say R, we'll say R, are thus at equilibrium. So their net rates are net equals 0. And we'll get to what I mean by that in just a moment. So why are we talking about this? Because we want to be able to derive mechanisms for catalytic reactions. It's when we're dealing with catalytic reactions, it's useful to know the reaction mechanism and the rate limiting step because it allows us to tune the catalyst properties to carry out the reaction more efficiently. So if one of my surface reactions is rate limiting, maybe I can find a catalyst that would more efficiently carry out that reaction. I can switch catalysts, which would allow me to operate at a faster rate and hence produce more product. One way to estimate the reaction is to run an experiment to get a rate law, and I'll talk about that in the next video. And then devise a mechanism and rate limiting step that explains the observation. So basically what we would do there is attempt to learn the orders of the reactants and products on the rate law. And then we would devise a mechanism and postulate a rate limiting step to try to replicate what we've observed experimentally. So we're going to do that now for this actual research example. The NO oxidation reaction, NO gas reacts with O2 gas to form NO2 gas, which occurs over a platinum catalyst. This reaction is important in NOx reduction. So NOx are NO and NO2 species. You'll see here where this doesn't seem like we're doing anything with the NOx to reduce it because we're basically taking one form of NOx and converting it into another. But certain NOx reduction technologies actually operate better when there's an equimolar amount of NO to NO2. So this reaction actually plays an important role in the reduction of NOx into N2. In fact, some of your vehicles probably comprise a catalyst that's carrying out this reaction. This is an actual research example. So in fact, this is an example the example that I worked on in my PhD at the University of Notre Dame. Because it's an actual research example and not a textbook example, we're gonna have some exceptions to the rule and complexities that wouldn't be present if this was a textbook or exam problem. Those problems, we write to be more straightforward so that students can practice with the concepts rather than having to practice with the exceptions to the rule. But it also provides a nice, I like to use this as an illustrative example because it's very well documented in the literature. So Fabio Ribeiro's group at Purdue has done a very nice job and very careful job on performing the experiments to get the kinetics for this reaction, which in part is what motivated my PhD thesis on using computational methods to hammer out the details. So the observed rate law for this reaction, so the rate of consumption of nitric oxide is first order in nitric oxide and oxygen, and it's negative first order in NO2. So what we want to do is devise a mechanism and rate limiting step that explain this behavior. So let's do that. So as a first step to that is thinking about the steps that we need to include in that mechanism. So what steps should we include? And we don't have to write out the chemical forms, we can just write them out in words right now, but what needs to happen for NO oxidation to occur? So for an NO oxidation to occur, one thing that has to happen is NO has to adsorb to the catalyst. So NO adsorbs to the catalyst. We also need O2 to adsorb to the catalyst. So now we've gotten our reactants on the catalyst. We showed in the last video that a key property of this catalyst, or it's one of its key roles, is going to be to break this oxygen-oxygen bond. So O2 is going to have to dissociate on the catalyst. So then, and we're going to say, we'll say to form two oxygen atoms. So now the oxygen atoms are going to react with NO. So NO star and O star react. To form NO2. And then we need NO2 desorbs from the catalyst. So it's the very minimum, these 5 steps must happen in order for the catalyst to carry out this reaction. So now let's write the chemical equations for those. So we'll say the first step, NO adsorption. So that's going to be NO gas plus star. Goes back and forth to NO star. And we're going to give this an equilibrium constant here. So we've said we're going to make the assumption that this is a non-activated reaction. We're going to thus also assume that it is not a rate determining step, and hence that it's allowed to come into equilibrium. So we're going to go ahead and write an equilibrium constant up here. Recall that the equilibrium constant is equal to the forward rate constant divided by the reverse rate constant. So this is identical to writing a forward arrow with a forward rate constant over it and a reverse arrow with a reverse rate constant below it. This is a capital K, and these are lowercase k. Okay. And again, recall that the stars are catalyst sites and the starred species are bound to the catalyst. So our second step, we're going to do the same thing for O2. Third step, we said oxygen is going to dissociate. This reaction is not an absorption-desorption reaction. It's a surface reaction. Because of that, we're not going to make the assumption right away that it's in quasi-equilibrium. So the way I'm going to write this reaction is like this. So I'm going to use this to denote a reversible reaction, or it's potentially reversible. We don't know. We're not yet making a decision about whether this reaction is reversible, irreversible, or in equilibrium. We're just going to give it the possibility to be any of those things right now. So I'm going to write rate constants instead of equilibrium constants on these arrows. These are lowercase k's, the forward rate constant and the reverse rate constant. And over here, I'm going to write 2O. And again, the reason for this is because this is a surface reaction, so it could very well be the rate limiting step. We haven't gotten there yet. We'll get there. We'll get to the point of making a decision about a rate limiting step in just a moment. Okay, so step 4. Now we said we're going to have NO and O reacting. And again, this is a surface reaction, so I'm not going to make a decision quite yet about what this reaction is doing. I'm just going to leave all possibilities open. And then my 5th step, we said that NO2 is desorbing. And now we can go back to the much easier scenario of assuming quasi-equilibrium, because this is a adsorption-desorption step. So note again here, in this mechanism, the sites must balance in each step. So I believe that we've done that. We can check. Yeah, so the one, I guess in this case, we have 2 sites over here. This is actually 2O star, so there's 2 oxygens bound to catalytic sites, so the sites do balance in all of the reactions. Okay, so now we have a mechanism, and now we need to see if the rate from this mechanism matches the rate that was observed experimentally. So how do we get the rate from this mechanism? So the rate of the reaction, we're going to make the assumption that the rate is approximately equal to the rate of the rate limiting step. So this is an assumption. And in fact, it's kind of like a model. So when we look at catalytic reactions, we are often assuming or using the model that the rate of the reaction is equal to the rate of the bottleneck step, and that all of the other reactions go pretty quickly. So the assumption there is that the catalyst, because you have a catalytic material, which is lowering the activation barriers and providing a lower energy route from reactants to products, the assumption is that it's doing that effectively for all of the steps except for one. Hence, the rate depends on just the rate of that one reaction. That is an overly simplified model, but in a lot of cases, it's useful. So, and it's for an introductory lecture on catalytic mechanisms, it's perfectly acceptable. So, really getting into more details than that is beyond the scope of this course. Yeah. So, when I give this lecture, I let the class choose which step should we choose as rate limiting, and then we work through the example. But given that this is an asynchronous lecture, I can't just poll the class and see which step you would like to assume. But let's look back at the mechanism. So we have 5 choices here, but we're immediately going to rule out steps 1, 2, and 5 because we're going to make at least the first assumption that those are, since they're adsorption and desorption, that they're not activated and that they thus are not the rate limiting steps. So that leaves us with 3 or 4, which can be the rate limiting step. One of the beautiful things about this reaction mechanism, which these are complexities that are beyond the scope of this course, is that under actual catalytic conditions, depending on the conditions you select, step 3 or 4 can be rate limiting. But we want to capture we want to assume the rate limiting step that's going to capture the observed experimental behavior, which was this rate law. So let's just pick, for the sake of this lecture, let's choose step 3. And I'm going to choose step 3 because oxygen is just really hard to dissociate. So I'm just going to assume that it is the rate limiting step. So if step 3 is the rate limiting step, then all other steps, including step 4, are assumed to be in equilibrium. So that means that their net rates are equal to 0. So under this assumption, the rate of NO consumption, RNO, is equal to the forward rate of step 3. So here we've assumed that step 3 is irreversible. So really what we're assuming there is that step 3 is so slow that it takes a long time for it to turn over. So it's really not even able to it's not able to produce enough. So the oxygen molecule is not able to produce enough oxygen atoms for it to even get close to being in equilibrium. So the chemical potential of absorbed oxygen just never really accumulates enough, and so that it would become in equilibrium with the chemical potential of absorbed O2. So that's what we're saying here when we say irreversible. So therefore, the rate of NO consumption is going to be equal to R3, which is going to be equal to K3. And this is K3 forward, but since I'm dropping the reverse, I'm just going to call it K3, times the coverage of O2 times the free site coverage. So here the thetas denote coverages. A coverage, it's basically like a concentration, but for a surface. So instead of the number of molecules in a volume, it's the number of molecules covering a surface area. Specifically, it's the number of catalytic species occupying a catalytic site divided by the number of catalytic sites. You could also say the number of catalytic species per unit area. We'll say per catalyst surface area. Okay, so going back to our mechanism, looking at step 3, what we did here was made an assumption that the step is elementary, that this is an elementary step, and that we should, whenever we write a mechanism, mechanisms are always comprised of elementary steps. So maybe we should go back and write that down now that we have the information to do that. So mechanisms are series of elementary steps. So when we break the reaction down into a mechanism, we're breaking it down into a series of elementary steps. So that rule is rarely ever broken. So when you're assuming a mechanism, always write out the elementary steps. So if we look at step 3, the elementary reaction for this, assuming that it's a forward reaction, so irreversible, is going to be the rate constant times the concentration of oxygen on the surface times the concentration of free sites. So that's what we've written down here, except instead of using C, concentration, which is number of molecules per volume, we've used theta, which is number of molecules per catalytic site, or number of molecules per surface area. So basically, instead of looking at a volume concentration, we're looking at a surface area one, because now we're looking at reactions on a surface. Okay, so going back to these thetas, so by definition, theta is bounded between 0 and 1. So in the case of the coverage equaling to 0, that means that you have 0 catalytic molecules that in the case of 0, that means you have 0 molecules adsorbed to your catalyst. In the case of 1, that means that you have 1 molecule occupying every single surface site. The surface is entirely full. The coverage is equal to 1. So another limit on the coverages is that if you take all of the coverages and you sum them, that must equal to 1. So, and this includes the free sites. So going back to our mechanism, if we took the coverage of NO and sum that with the coverage of O2 and sum that with the coverage of atomic oxygen and with the coverage of NO2 and then added that all up along with the remaining free sites, then we would get that would all be equal to 1. So we can't have any other number. Once we sum all of the coverages, including the free sites, the value must be 1. And that again is site balance. So this is okay, so let's test our assumption that step 3 is the rate limiting step. So to do that, we need to see if this rate law can match the experimental values, or the experimentally observed rate. So to do that, we need expressions for theta O2 and theta star. So it's difficult to measure coverages of catalytic species under reaction conditions. So instead of measuring them and knowing them, we need expressions for them. So we're going to write expressions for those using our mechanism. So we're going to write the expressions using the remaining steps and that would be 1, 2, 4, and 5 in the mechanism. So first, let's do theta O2. So we're going to get that from which step? Which step do you think we will use to get that one? We're going to get that from step 2. So if you recall, step 2 is O2 adsorption. So we're basically going to assume that the O2 on the surface is in equilibrium with O2 gas. So assuming that this step is in equilibrium, the net rate is equal to 0. And we'll say R net 2, which is equal to R forward 2 minus R reverse 2. And again, if we write these as elementary steps, this is going to say the rate constant, the forward rate constant of 2 times the pressure or concentration in the gas phase times the coverage of free sites minus Kr2 times the coverage of O2. Or alternatively, since I had already made the assumption, so this is the full way to write this out, but I would already made the assumption that this reaction was in equilibrium. Because of that, if I set this equal to 0 and I solve for O2, I'm going to come up with an equilibrium constant. So in that case, I would have theta O2 is equal to K2. This is the same K2 we wrote above here. Times the concentration of O2 in the gas phase times the free site coverage. So now I have my expression for O2. Now I need my expression for theta star. So theta star, the coverage of free sites, the way I get that, so theta star is through the site balance. So theta star, I know from the site balance, is equal to 1 minus theta NO minus theta O2 minus theta O. And that's it, right? That's all my, minus theta NO2. So that means if I can come up with expressions for theta NO, theta O, and theta NO2, I know I can get my free site coverage. So now I have to get all of those values. Theta NO, I'm going to get from step 1. And that's going, and I'm going to do that the same way I got for theta O2. Oops. Theta NO2, I'm going to get from step 5. This is a desorption reaction, so it looks a little bit different. So now I need theta O. Really, the only step I have left with which to get theta O is step 4. And that works because I already have expressions for NO star and NO2 star, or theta NO and theta NO2, hence I can use those to get theta O. So I'll say I'm going to get this from step 4. And remember that this is all a model, so we're going to test and see if the model is valid in a moment. So as you're going through and doing these things, there's no clear indication that this is the right way to do it, but it works. It works. So let's try it and let's see if once we've constructed the mechanism this way, if it fits the experimental data. If it does, excellent, our model works, and we can go on. If it doesn't, then we have to go back and maybe redo our thinking or our analysis of the mechanism, and maybe even redo our mechanism. But at this point, don't get held up because you're not sure whether this is the right way to do it or not. You're not supposed to know that quite yet, so we haven't gotten there yet. Okay, so step 4 we've also assumed is in quasi-equilibrium, so we can write the coverage of oxygen using that information. In doing that, we're going to get theta NO2 theta star divided by K4 theta NO. And we want to get rid of all of these thetas, so let's substitute in our expressions for theta NO2 and theta NO. In that case, we would get CNO2 theta star divided by K4, K5, K1, C, and O. So now I can substitute that all in, so therefore theta star equals 1 minus K2 CO2 theta star minus K1 CNO theta star minus CNO2 theta star divided by K5, and minus, so this is O2, NO, NO2, so I need my oxygen coverage, CNO2 theta star, K4, K5, K1, C, and O. So now I need to, I basically just need to do some algebraic manipulation, and I can solve and get an expression for theta star. Some keys when you're doing this: you should have all of your expressions should have, if you've done your site balance properly and you've written your reactions as elementary steps, all of these expressions, also if you've done your algebra properly, which I should ask you to check mine because there's always a possibility to make algebraic mistakes. But anyways, you should have each expression, except for the first one, this one, should have be multiplied by theta star to the first power. So you shouldn't have any other powers, second power, negative power. They should all be multiplied by theta star. So no other expressions of theta star. If you don't have that, then go back and check what you've done, because it's likely that there's been an error along the way. So when you have an expression like that, that makes it easy to solve or to get an expression for theta star. Theta star is equal to a 1 divided by 1 plus K2CO2 plus K1CNO plus CNO2 divided by K4, K5, K1 CNO plus CNO2 divided by K5. So that's my expression for theta star. So now I can rewrite rate expression. So in other words, I'm going to rewrite my rate of consumption of NO for this example. And when I do that, I get minus R NO is equal to the K3 lowercase times K2 uppercase CO2 divided by 1 plus K2CO2 plus K1CNO plus CNO2 divided by K4, K5, K1 CNO plus CNO2 divided by K5 squared. So let's pause here and look at this rate law. So when I do this, if I recall how I got this expression here, so this is my free site coverage squared. So basically this term here. So if I remember where all of these terms came from, this one is theta star divided by theta star. This one is theta O2 divided by theta star. This one is theta NO divided by theta star. This one is theta O. And this one is theta NO2. So why this is important, this rate law obviously does not fit the experimental data. I need to do some manipulation of it. And when I do that manipulation, I'm going to make assumptions about the various coverages and how they're affecting the rate law. So some of the coverages I'm going to assume are very low, so almost equal to 0. And so I'm going to knock those terms out of my denominator. And some of those I'm going to say they're higher, so maybe closer to 1. So those coverages I'm going to keep in my denominator. And that's how I'm going to make my rate law look closer to what is observed experimentally. So to do that, I'm going to make some assumptions. Assume. So one thing for sure, I know that if I go back to my observed rate law, I know that I want to be first order in NO and first order in O2 and negative first order in NO2. So I already am first order in O2. So that's a good thing. I want to leave that the way it is. So this term, I'm going to assume I'm going to make that go away. I don't want that term in the denominator. It's going to ruin the fact that I've already gotten first order dependence on O2. So I'm going to assume that theta O2 is approximately equal to 0. And when I say that, that tends to cause a small problem because we've said that for my rate to occur, so my rate of reaction, we've said this is a rate limiting step, and we need this rate to be happening, otherwise the reaction isn't happening. So if this is the coverage of O2 is truly equal to 0, that means that the whole rate of reaction would be equal to 0 because there would be no O2. But I'm not saying that the coverage is identically equal to 0, I'm saying it's approximately equal to 0. So it's small enough that it's not going to affect the rate order, or the reaction order of O2 in this rate expression, but it's not so small that the rate isn't proceeding. So maybe a better way to say that is, so actually what we're saying is that theta O2 is much less than the coverage of free sites. So if this term is standing, we're saying that theta O2 is much smaller than that. Okay, so that gets rid of that term. We're going to say that then this is approximately equal to 0. So we're going to knock this term out of our denominator. Another term that we're going to knock out is this one. So we have first order dependence on NO. If we were to keep this term in our denominator, then we would have negative first order dependence on NO, which is incorrect. So let's assume also that theta NO is approximately equal to 0. And again, we're not saying 0, we're saying approximately equal to 0, or theta NO is much less than theta star. So now I have two coverages left. I have my oxygen coverage and my NO2 coverage. Both of those give me the behavior that I'm looking for in terms of NO2. So both of those put NO2 in the denominator of my rate expression. However, only oxygen puts NO in the numerator. So I'm going to assume, for the sake of simplicity, I really just want to be dealing with one dominant catalytic species. So one species is present on the surface in large quantities and all the rest are small. So that, again, is a model, it's in its assumption. It may work, it may not, but it's a good first assumption or first guess when we're working with mechanisms. So one dominant surface species, all of the rest of the species have coverages close to 0. So I'm going to say, since oxygen is the one that works better with what the observed behavior is, I'm going to say that oxygen is the dominant surface species and NO2 has a very small coverage. So we're going to also assume that theta NO2 is close to 0. In other words, theta NO2 is much less than the coverage of free sites. So I'm going to assume, so actually let's just say, so the fourth assumption is that oxygen is the most abundant surface intermediate, or surface species. And I'm going to assume this because it gives a negative order in NO2 and a positive order in NO. So let's make the note here also. Often we assume 1. In fact, let me write that out. 1 MASS, most abundant surface species, and that coverages of all other species are approximately equal to 0. So if we do that, that means that this term goes to 0, this term goes to 0, this term goes to 0. I'm left with just this term and this term. I can make one more assumption that theta O is approximately equal to 1. And again, it's not going to be equal to 1. It's going to be close to 1. But what this does is means, we'll say therefore theta star is approximately equal to 0. So I know that makes these statements all confusing, but if you think about, in this case, we'd be saying maybe the coverage of oxygen is like 0.92 or something like that. So it's close to 1. That means the coverage of free sites is maybe 0.08, and the coverage of all of these other species are 10 to the minus 6, right? So in all actuality, theta O is probably closer to 0.999, theta star is equal to 0.001, and all the rest of these coverages are equal to on the order of 10 to the minus 6 or something like that. So that allows for the rate to still be going. I still have free sites available to carry out the reaction. There's just not very many of them. These are all have small coverages that are not going to be recognized when I solve this rate, but they are appreciable enough that the rate proceeds. So that's when I make these arguments, that's kind of where I'm thinking. So if I do that, now I can rewrite again. The rate of consumption of NO is equal to K3, K2, CO2 divided by CNO2 squared divided by K5 squared, K4 squared, K1 squared, CNO squared. And so another thing that I do when I look at catalytic mechanisms, I have way too much information here. Actually, I don't. So if I had a quantum mechanics tool, I could determine what all, or I could make an estimate of, or a good hypothesis about what all of these rate and equilibrium constant values are equal to. But really, if I'm looking at experimental data, I don't have the ability to discern each one of these individually. And in fact, I could do that. Well, I couldn't. I'm not an experimentalist, but people have done that. It's literally taken decades of work, multiple research groups, and a lot of very nice techniques to be able to discern all of these, and in fact, combinations of experiments and theory. So it's possible, but it's not something that we're going to be able to do routinely. So instead, we tend to lump constants together. So if we lump constants together, we're basically just going to say, well, I'm going to, take this denominator, I'm going to put it up here. Now I have a whole bunch of constants lumped together, and I'm just going to call those equal to k. So then we're going to rewrite or simplify, we'll say. So we're just going to say that Rno is equal to k. This is a rate constant. I know that there's equilibrium constants embedded in there. They're just basically multiplying or dividing the rate constant by some value. So we're going to call it a rate constant times CO2 CNO squared divided by CNO2 squared. So I'll say where K equals K3, K2 divided by, or it'll be here. We'll say where K equals K3, K2, K5 squared, K4 squared, K1 squared, and is a rate constant. So what we need to be aware of here is that it would be the rate constant for the overall reaction. So it includes this coverage dependence. It's not the rate constant, the forward rate constant of reaction 3. It's the forward reaction of rate 3 multiplied by the coverage dependence of the rest of the species in the reaction. Okay, anyways, this gets us an expression that we're used to looking at. So this one right here, this power law, we now have a power law model. As you'll notice, we wanted first order dependence in O2 and first order dependence in NO and negative first order dependence in NO2. We got first order dependence in O2, second order dependence in NO, and negative second order dependence in NO2. So we're not quite there yet. If this was your research, then your job now would be to go back and modify this mechanism and also the assumptions that were made. And in fact, that is largely what I did in my PhD thesis. What we ultimately found was that, as I alluded to before, the behavior of the reaction, sometimes this step is slow and sometimes this step is slow. That depends on the coverage of oxygen. At low coverages of oxygen, this step is rate determining, whereas at high coverages of oxygen, this step is rate determining. In reality, the rate determining step is actually O2 adsorption, and that's how we end up getting this first order dependence in NO2 and NO. The reason there is because I only have one in my forward step. I only have one site, so my theta star ends up not being squared. It's just theta star. So that is, 5 years of PhD work for me in a collaboration with people at Purdue. So a lot of work, certainly beyond. You'd have to be working on this like all day long, every day for about 5 years to be able to come up with that. So it's certainly beyond the scope of this course. So in this course, if I were to give you this example, then to solve in a textbook or on an exam, then the observed behavior, this expression would have been CNO, or would have been K times CNO squared times CO2 divided by CNO2 squared, which would allow you to write a straightforward mechanism and come up with a straightforward answer. But again, I wanted to show you a research example to kind of talk through some of these things. But we're not going to go back and do all of that work to get this, to make this look like experiments, because it just involves too many exceptions to the rule that are beyond the scope of this course. Now, if you're solving a problem in a textbook problem or an exam problem, those are straightforward. So there is a mechanism that with straightforward rules, no exceptions to the rule. So if you get something that's different than observed, that means you probably need to go back and make a different assumption about your rate determining step. So pick the other surface reaction. I don't think any of the examples in this book have adsorption-desorption reactions being rate limiting, because that's kind of an exception to the rule. And if you want to see the full story on this one, there's a paper by Shadab Mullah from Fabio Ribeira's group in Catalysis Letters. From 2005. And you can see how they rationalized the observed behavior. So that's all I want to say for this lecture.